Welcome back. In this class, we will discuss something about relaxation, like spin lattice and spin-spin relaxation in NMR. Of course, this is a vast topic. One can discuss this for several hours, or several days and weeks. We can talk about it. It's a huge topic and a very difficult topic to understand. But I will try to make it as simple as it is for you, so that you can try to get the concept of what is T1 and what is T2. Okay, that's what is the important thing. And at the end, I'll give you how to measure T1 and T2, some experiments, so that you'll get a feel for what is T1 and T2. Because this is very important. See, T1 and T2 values provides information about the dynamics of the molecule. You may at many times come across situation where you want to measure the T1 and T2 to study molecular motions. So better to have some conceptual idea. Quickly, probably in this class, I will try to tell you what is T1 and T2. Okay. We'll look at the relaxation mechanism first, and then later their measurements. Let us say we have the sample in the absence of a magnetic field. This we have been discussing since the class 1. There is no net magnetization. Nuclear and magnetic moments are randomly distributed inside the sample of NMR tube. Okay. So there is no net magnetization. Now I am going to take the sample, put it in a magnetic field. What is going to happen? As you know, once it is placed in a magnetic field, it starts beginning to align slowly. It has to align in the direction of the magnetic field. Or in other words, we call it polarization in the direction of the magnetic field. And we generates net magnetic moment, net magnetization. We discussed about this, which is called bulk magnetization. Okay, this is the situation. These are all net magnetic moments, which are in the two spin states alpha and beta. And we have been discussing many times. We have more spins in the direction of the align in the direction of the magnetic field than in the direction opposite to that of the magnetic field. It is a statistical average, not that the spins are always along this axis. On an average, if you take, there is a tendency for more spins to be in the direction of the magnetic field than in the direction opposite to it. As a consequence, we discussed about the bulk magnetization, where you have the magnetization, there is, because of the random phase approximation, there is no magnetic moment component in the XY plane or in the transverse plane. You are going to get the magnetization vector in this direction and in this direction. The vector addition of these two results in a sort of a net bulk magnetization. This we understood long back. This is a net magnetization. You can treat like a tiny magnet. That's what we said. So now there are two energy states. Now because of these two we discussed, and alpha and beta states. So there is more population in this state, let's say, in the ground state than in the higher energy state, than in the lower energy state, right? So how this population difference occurred? We should understand that. First, conceptually, how did this population this difference, spin population difference, occurred as soon as you put this sample in the magnetic field? Let us, to understand, for the two energy states like this, alpha and beta, let us say number of population in the alpha state we denote as N alpha. Number of populations, spin population in the beta state, we define as N beta. This is, we are defining number of populations given by N for alpha and beta. Now, because initially, before putting into the magnetic field, there was no preferred alignment, there is no polarization. Now, when the polarization has to occur, we have to understand the spins has to redistribute themselves between the two energy states. Let us define W alpha beta and W beta alpha are the probability of the transitions from alpha state to beta state, that is upward transition, and from beta state to alpha state. The spins, when it has to polarize itself, some spins are going from here to lower energy state to higher energy state, and some will come down from higher energy state to lower energy state. As a consequence, there is some difference of population. But what is the probability of this transition? Let us define by these two terms, W alpha beta and W beta alpha for upward and downward transitions. It is a definition. We are defining that. It has to be now W beta alpha has to be larger than W alpha beta. You know why? That is the only situation you can see when W beta alpha, that is from downward to upward, probability to transition from alpha to beta, beta to alpha. Okay, alpha to beta, beta to alpha. So this one, W beta alpha, has to be larger. Correct. If that is probability of transition from upper energy state to lower energy state, from higher energy state to lower energy state, that probability of transition, when it is high compared to transition probability from lower energy state to higher energy state, from alpha beta to beta, alpha to beta state, probability, it should be lower than this. True, right? It has to be. Otherwise, system cannot develop net polarization. Because of this condition, W beta alpha, probability of the spins coming from higher energy state to lower energy state is more than this, there is a net polarization developed in the spin system, right? Now, when the sample reaches thermal equilibrium, what is going to happen? It attains thermal equilibrium with the surroundings. Then there is no more change in the system, no more change in the net magnetization. It has reached, the population between alpha and beta states has attained what is expected from the Boltzmann distribution. Okay, it has population of alpha and beta states now corresponds to Boltzmann distribution, and there is no more change in the net magnetization. Now, also the spins are uncorrelated in space, especially in the transverse plane. That is also true. We discussed that all the spins in the transverse plane gets uncorrelated. That means we also discussed this long back. There is no net magnetization in the XY plane. That's true. That is because conceptually we discussed this long ago. Now, that is one natural situation as soon as I put the sample in a magnetic field. It attains thermal equilibrium, and we discussed what is the transition probability between two energy states, and we understood this should be our assumption is that W beta alpha should be larger than W alpha beta for developing net magnetization. Correct. Now, in the other situation, like when we are collecting the signal, we send a radio frequency pulse in a direction perpendicular to the magnetic field, bring the magnetization to X transverse plane. Understand? And then you start defacing in the transverse plane. At the same time, start growing along z-axis. That's what we discussed long back. Because system has to attain thermal equilibrium. The magnetization has to go back to thermal equilibrium. There are certain processes which are responsible for that. Okay. Then also, it takes some time to attain thermal equilibrium. Okay. You perturb the spin system from equilibrium. Then after some time, if you leave it like that, it has to go back to equilibrium. What is the time it requires to go to thermal equilibrium? Exactly, it is similar to what I said. As soon as you put this sample in a magnetic field, it requires some time to attain to get net polarization, right, in the magnetic field. That's our time which is required for that to attain net polarization in a magnetic field even before applying RF pulse. That is spin lattice relaxation time. That is a relaxation time. Same thing here also. The time required for the magnetization from a perturbed state to come back to thermal equilibrium to along the z-axis is what is called a relaxation process. Okay. There are two types of relaxation. We'll go ahead and understand. This is one type of relaxation where magnetization has to come back and grow along the z-axis. Of course, as I said, there is no correlation no magnetization in the XY plane because they're uncorrelated in the transverse plane. That's all I already told you. The process that brings the spins to thermal equilibrium is called relaxation. That's what just now I said. Now, let us try to do simple mathematics. Well, not a great mathematics. We don't need to worry too much. We'll go very simple what you know. The basic assumption we'll make two assumptions. One, the rate of transition from alpha to beta is that it is proportional to the population of alpha state. The rate of transition W from alpha to beta, W alpha beta, we say is proportional to number of spins in this alpha state. Number of spins is n. So W alpha beta we say is proportional to n alpha. That is the first assumption. Second, we say it is a first order process with a rate constant. This is a simple assumption we do. Now we understand what is the rate of change of population in state alpha and in state beta. Okay. So rate of change of population of state alpha is defined by W alpha beta. That is what the transition probability. Rate of change of population of state beta is W beta alpha. Now with these assumptions, let us try to work out what is the total rate of change of population of the state alpha and beta. Now, how much is the change of population in alpha state? It is given by the equation alpha is equal to minus W alpha beta plus beta alpha. What is the meaning of that? The probability of the spins coming from a higher energy state to lower energy state is more, and this is negative because at the same time there is also possibility the spins from the lower energy state goes to higher energy state. When it goes from alpha state to beta state, it is a loss of signal, loss of population in alpha state. When the spins come from beta state to alpha state, there is a gain in population for alpha. That is why for first probability is negative, second probability is written positive. You understand? When the spins come from higher state to beta state to alpha state population goes up. So that is plus. But at the same time, spins also go from alpha to beta. Then it's a loss of magnetization. Okay. So this is why these two terms represent this, taking probability of the population that transition from alpha to beta, beta to alpha. Now we can define a rate equation for the state alpha. What is the rate equation? The rate of change of population, I said, is proportion. The rate of transition is proportional to n alpha, I said. Now the rate equation, if right, as a function of time, the change of population as a function of time, rate of change of population is given by simple expression n beta into W beta alpha minus n alpha into W alpha beta. It means number of populations from beta is coming down using this probability to alpha. At the same time, some spins from alpha goes to beta with this probability. This is what it is. Same thing we wrote as a function of rate equation here, where total number of population each state alpha and beta is taken into account. Now the rate of equation for state B is identical. Only thing is you have to change the sign. That's all. For beta, when this goes up, this adds up. When it comes down, it is a loss of population in beta state. Except for the change in the equation is similar. Okay. Now another thing. What is the thermal equilibrium situation? At thermal equilibrium, populations are not changing. It has attained Boltzmann distributions and then no more change of population. That means at thermal equilibrium, the rate of change of population in state alpha or beta, whatever you take, should be zero. That's correct, right? There is no rate of change of population, so we call it zero at thermal equilibrium. Now go back to this equation. Now put it as zero. Equate it, this term to zero. That's what we do. And we calculate. Now, if we equate this thing, what is going to happen? When it takes at thermal equilibrium, there is no more change. No more change. This is completely both are equal, this implies that at equilibrium, N alpha should be equal to N beta. This is something strange. Okay. N alpha has to be equal to N beta so that this term goes to 0. This goes against our assumption or goes against our conceptual understanding. This is incorrect because there is a population difference even at thermal equilibrium. Okay. There is no rate of change of population is not there, but does not mean there is no difference in population. But it says there is no difference in population here. So this equation is not correct. How do you overcome this situation? Now, let us do one trick. You, instead of taking the population difference, we will treat it as a deviation of the population from the equilibrium value. That's something we define. Equilibrium value is at N alpha 0 we consider. N alpha 0 is the equilibrium value. The deviation of the population from its equilibrium value is called N alpha minus N alpha 0 to the power N alpha superscript 0, where N alpha superscript 0 is the equilibrium population of the state alpha. Okay, this is equilibrium population and this is the total term, the deviation from equilibrium. Same way you can define for beta state also. Now put that into the equation, rate equation. So instead of putting just N alpha and N beta, we substitute with these two terms. That's all we did. Similarly, you do for the beta state and do a little bit of jugglery equating these two terms, these two equations, and you can find out what is the rate of change of Z magnetization. That is given by d by dt of N alpha minus N beta. We can work it out with this, and simple mathematics you can do. It is not a great mathematics, simple rearrangement of the terms and arithmetic. Then you find out mz of 0 is equal to N alpha 0 minus N beta 0. This is the equilibrium magnetization. Understand? Equilibrium magnetization is N alpha 0 minus N beta 0, and the rate of change of mz correspond to this one. Okay, that is simple mathematics. You don't have to worry. Finally, you understand dmz by dt correspond to this term. Okay, and whereas this one is already defined as equilibrium magnetization. What is T1 here? T1 is a rate constant. We have defined this as a new term called rate constant. Now, what does this equation say? The rate of change of magnetization is proportional to deviation from its equilibrium value. Like individual state, we found out what is equilibrium magnetization. We said N alpha 0, N beta 0. But for the entire magnetization, when we consider, the equilibrium value is mz 0. And the deviation from equilibrium is mz 0, mz minus mz 0. Okay, that's what this equation says. Now I put mz equal to mz 0. What happens? When mz equal to mz 0, that is the equilibrium. There is no deviation. Okay, there is deviation from the equilibrium value is this one. When these two are equal, this term becomes 0. There is no deviation from the equilibrium. Then mz equal to mz 0, the system is at equilibrium, nothing happens. Okay, that's what we want, we were thinking, right? So mz deviates from mz 0, there will be change of mz, and this rate will be proportional to the deviation from this one. Further, when there is a change of the magnetization, it will return to mz from its equilibrium value. That is an important term, remember. Okay, so now put this equation, you try to do some jugglery. You can integrate this equation and everything and find out what it is. Do some rearrangement of the mathematics here. Then you get an exponential term here. Okay, the magnetization, how it returns to equilibrium when it is deviating from equilibrium. But after some time, it will come back to equilibrium by an exponential function. The time constant for the exponential is given by T1. This time constant, this is the time that is required for the magnetization which is deviating from equilibrium to attain thermal equilibrium, to reach thermal equilibrium, is called spin lattice relaxation time. are also called longitudinal relaxation. For the magnetization to come along z-axis, this is the time constant. Okay. So this is how it says. Look at this in the diagrammatically. See, that's a simple basic mathematics. I mean, of course, in the whiteboard, if there is anything, I could have written every step and worked out and for you. But since we cannot do it online in the computer terminal, so I'm just giving you the idea. This type of expressions should be discussed only on the blackboard or whiteboard so that we can discuss everything. We can work out the mathematics. But I went through the mathematics as don't worry, it's not a big mathematics. Simply you have to understand the deviation from the equilibrium magnetization was given a term, and we know what happens, how it attains thermal equilibrium. It needs a term called T1, which is an exponential term was introduced, and the constant of that is T1, the time constant. That is called spin lattice relaxation time. That's what is the concept. Now look at it. When the magnetization is completely dephased here, before that, see what is happening? The magnetization is brought here to XY plane, and slowly they start dephasing. While dephasing, they also start growing along z-axis. Slowly, this is spins which are dephasing, and now you can work out the total magnetization. Initially, it will be 0. At magnetization, dephase bulk magnetization along z-axis is 0. This is magnetization along z-axis. As soon as you bring it to XY plane, there is no magnetization in the z-axis. Please understand. And slowly it is dephasing. At the same time, it is growing along z-axis. Goes on and on and on. When it is completely dephased in the XY plane, then magnetization would have completely grown along z-axis. Exactly like a animation shown here. It starts dephasing, slowly goes along this stuff. And here the spins will start losing the energy and give the energy to the system. Because you have already disturbed by giving a radio frequency signal, it has gained energy. And the system has to attain it to equilibrium, means it has to give energy to surrounding or somebody. And it loses energy and attains go to thermal equilibrium with this time constant. Okay. Now this is the process. What happens slowly, if you understand, T1 relaxation process is like this. Bring the magnetization to transverse plane and start dephasing here. Slowly it goes here, goes here, goes here, and after a time constant, it completely recovers along z-axis. Okay. And there are certain terms defined for this. Some synonyms are there for this. That is T1. It is called spin lattice relaxation, or called T1. Also called longitudinal relaxation. Also called thermal relaxation, because it attains thermal equilibrium. So there are certain synonyms for this. In the books, they use varieties of various terms like this. T1 relaxation, longitudinal relaxation, growth along z-axis, spin lattice relaxation, all those things, but everything is conceptually same. Now, as the longitudinal magnetization grows to m0, it has to lose energy, I said. Then why should it lose the energy? Because statistically, more spins are favoring the lower energy, that is spin up orientation, than other orientation. So as a consequence, it has to lose some energy. Okay. And important point to remember, spins do not actually reside only in the spin up states. There are spins in both alpha and beta states. But the only thing is, the average expected value of this, all the spin angular momentum taken together, there is a probability more spins are in this direction. That's all. Not that you can't say that there are no spins in beta states. It is there. Probability is more along this axis. That we have been discussing many times. Okay. So spin systems start losing energy because the more favored orientation, there is excess spin in one of the states. For this relaxation to occur, I said energy must leave the spin system. This energy, when it leaves the spin system, I said here, energy, the energy of the spin system must decrease. Not only decrease, it has to leave the spin system. Okay, it leaves. Where does it go? It has to go somewhere. And when you give out the energy like that, somebody has to take that energy, and something should happen to that whoever takes the energy. And this energy loss is not recoverable. It's a one-time loss, keeps going. It's unidirectional. How does it loses the energy? It takes energy and give it to somebody in the form of heat. It is sort of a transfer of heat. And this one generates heat to the person or the surroundings which gives the energy is so small, it does not get noticed at all. Because it leaves out heat and comes back to equilibrium. That is the reason why T1 phenomenon is also called attaining thermal equilibrium. Understand it? There is energy loss which is unrecoverable and which represents transfer of heat. So this phenomena is called thermal equilibrium because of this reason. It gives out energy in the form of heat. Now the question I still have to answer, where does this energy get transferred? Where does this energy get transferred? It always gives energy to nearby nuclei, atoms, molecules, some other spins. It need not be J coupled or anything. Any surrounding species, anybody who is surrounding that spin, anyone, everything is enough. It can give rise to transfer the energy to neighboring nuclei, neighboring spins, neighbor atom, molecules, etc. How? Through collisions, rotations, and various types of electromagnetic interactions. It all can happen, any of them. It can collide with other atom and gives energy. It can undergo molecular rotation and gives energy. And it can undergo electromagnetic interaction. So all these things are there. These are the modes through which it will give energy to the other people, other person who is absorbing the energy. And what do you call that? The person, the system which absorbs energy, which is given by the spins, is called lattice. Lattice is not, you don't think like crystal lattice. Any external environment for this nuclei of interest, which absorbs energy given by the spin, is colloquially a term called lattice. Okay? T1 relaxation simply an energy flow between spins and lattice. Lattice is nothing but anything surrounding that spin is called a lattice. It's simply an external environment. So what do you mean by that? Relaxation is nothing but an energy flow, especially T1. Energy flow between spins and lattice. That's all. You please understand, relaxation is the energy flow between spins and lattice. That is T1. But how much is the energy transferred from this nuclei? I already said it's much, much, much smaller than the kinetic energy. Normal molecular kinetic energy, there is a kinetic motions going on. Thermal motion is always there. Compared to that, it is much, much smaller. So it largely goes unnoticed at all. At room temperatures, it largely goes unnoticed. And this heat quickly gets dispersed into the system. Now the question is, fine, it also happens. But how does this emission occur? How does energy emission occur? You can't simply give the energy to somebody just like that. There must be a medium for it, right? So how does this energy emission occurs? Of course, one of the thing is you can consider the lattice energy state and spin energy state. When spin, it has to give the energy, and if let us say it has gained energy and gone to excited state. If it has to come down, it will give energy to the lattice. The lattice will go up here. The spin of the lattice will go to the excited state. But then, how does it come down? Can it come down from excited state to ground state, from beta to alpha state spontaneously? No. Remember earlier also we discussed the spontaneous emission in the radio frequency region is almost negligible because it goes to the cube of frequency. I already told you long back. So all energy emission in NMR especially must be stimulated. There must be a stimulated emission so that this nucleus can give energy to the other surroundings. And What is the stimulation? Where do you get the stimulation from? The nucleus, if it has to give energy by stimulated emission, there must be some stimulation. Where do you get this? This is the stimulation comes because of the encounter of the nucleus with another fluctuating magnetic field. Where do you get that fluctuating magnetic field? It comes because of molecular motions. See, molecule keeps oscillating, keeps rotating, it's changing its state, and it undergoing fluctuation. So this fluctuation frequency is at the Larmor frequency, because it has to match the energy separation of the spins. Then only you can make sure the transition in the lattice takes place. The spin energy is given to the lattice, so the lattice will go up. Okay, so it must match with the Larmor frequency. The fluctuating magnetic fields have to match with the Larmor frequency. Okay, and without that fluctuating magnetic field, without that source, spins do not relax at all. And it is necessary to induce relaxation. And this source could be another proton, electron, or any nearby molecule. Okay, so like if you apply a radio frequency pulse and excite spins to give resonance, same radio frequency fields causing relaxation must also fluctuate near the Larmor frequency. Remember, I said when we apply radio frequency field, it must be an oscillating field, I said. Static will not work. That's what I said. I very well remember. So similarly, this also should be oscillating. The fluctuating field must be at the Larmor frequency, the transverse plane. Now, the question is, what is the difference between this B1 field, which excites spins, and fluctuating field that causes spin relaxation? Okay.